Thank you. It's my pleasure to introduce Amir Ahmedi from the Hebrew University of Jerusalem, who's going to talk to us on seeing colored images with music using the EYEMUSIC from perception to visual rehabilitation, with a commentary by Derek Brown.
Hi, it's a pleasure to be here. Actually, I'm standing here, but I'm representing the work of the team, and I will try to refer to the specific work of each one. This is going to be another neuroscience and behavioral talk. So in a way, it relates in different junctions, as you would see, to the work that Maurice was presented, but using other means like natural tactile stimulation and auditory sensory substitution. And it's going to have two halves, and we are going to talk about it. So the first question I'm going to tackle is, can the blind learn in adulthood to process visual information conveyed indirectly via a different sense in a new manner? And what I really would want to try and stress is to ask how far can we push it using explicit training and more experience with the statistics of the world. We'll try to tackle and see if we can generalize from 2D to natural environments, at least behaviorally. And then we'll ask what happened in the brain without visual experience when you learn to interpret SSD input implicitly, explicitly, using sounds, using natural sounds or braille. And if I would have time, I would try to relate all this to what actually ended the previous session with what is the relations between trying to do this sensory substitution non-invasively and how it relates to clinical intervention of trying to restore vision. The talk is going to have two parts. One is using the voice system, which is the veteran visual to auditory sensory substitution. But this time we are going to look at data of what we try to do now more organized in the lab is to try and image the brain as the training goes on. So initially I'm going to present you results after the full training, but from a couple of points, we already started to have data of trying to see the changes in the brain and the behavior after a few hours after the training begins, and then to trying to see if what happens when you are moving to full. And then in the second part of the talk, we are going to I'm going to show you a couple of recent experiments, some of them not published, using the color, adding color basically to this approach. So I want to start with two quick movies, which basically start to try to look at our approach, which starts with practice in front of the computer, what I'm going to show you soon, but then quickly after, for each lesson and each approach, we try to have starting interacting with objects and with the environment more naturally. And I think it's best depicted in the cases of faces. So this is basically after close to 60, 70 hours of training, and it basically shows how the training basically is built. So the training starts with very, very simple features. Oops. I had a feeling that something is going to go wrong today. I'm not sure why it's not working. Maybe we'll give it another, maybe the presentation is too heavy.
זה אף.
אוקיי, מאוד.
שומעים את שני המחיריים.
איך אתה שומע את המחיריים?
So this is Shlomo. He's a congenitally blind person, like most of our subjects.
שומעים את העיניים ואת האף.
יפה. ואתה שומע פה אולי עוד משהו?
נראה לי שגם הגבות מופיעות.
מעולה, כל הכבוד. בוא תנסה עכשיו להקריא.
העצוב זה השני.
מאוד. כל הכבוד.
And then in some of the subjects, we are able to try and generalize this. So try to, first of all, learn the shapes of various facial expressions. You can see here, Hamutal is wearing the setup of, and you can see here the voice by Peter Mayer, the reconstructions.
מעולה. עכשיו אנחנו קצת. עכשיו. מעולה.
And then to a different person, generalization. And this is running in real time.
לפי מה?
And it's go on and on. And what I would like to stress is that we try to work in this gap of and I completely agree here that even though the fact that the voice is basically trying to reconstruct the 2D image, just like in vision, we had a lot of room for cognition and experiences to change our perception dramatically. I like to give, and I think Jonathan Cohen gave several beautiful examples of how a single instruction or semantics or experience can change your cognition dramatically. So I think it leaves a lot of room to how we can work with these blind individuals. I like to give this example because it happened to me spontaneously, and usually, and basically I looked at this logo hundreds of times, and then suddenly one day I noticed there is an object within the E and the X. So, and usually about half of the audience see for some reason only when he gets this instruction, this arrow. So how many people see here the arrow between the E and the X for the first time? For the first time here. So it's a half. Now the thing is that in a single trial, your brain change forever in the sense that you would always see now this arrow. That's one. And probably you also remember this talk after that when you see the FedEx truck in the street. And this is, again, I want to stress this is one trial and changes your whole visual perception, object recognition, etc. So I think here we have a lot of room to work with all this machinery in the brain that do these type of things. Maybe we don't know to do it in the right way. Maybe we have to learn slowly. Maybe the rules are very different by learning that this is a bistable image, etc., etc. Maybe in some cases, some things are innate and constrained by the system, just like the examples of the inversion effects. You can have the same on the Mona Lisa. But this is a room, and give us and then by interacting between this bottom up, trying to in a low resolution represent the sensory part using the sensory substitution, and then adding all these experiences, statistics, heuristics, etc., etc. Maybe we can push this a few steps further. Okay. Now, one thing that interested us recently is the question which is critical to try and build, for example, this ability to understand faces or objects in different angles, etc., etc. And this is the issue of visual parsing. And visual parsing is basically a very basic ability to be able to segment and differentiate various objects. And it's a huge problem in sensory substitution because usually in most of the studies you would see one object. It will be usually 2D, maybe it will be 3D, but the ability to start and differentiate and build a more complex scenery is something very basic that we will have to face if we will want to reconstruct vision using this approach. And very interestingly, there is this project Prakash by Pawan Sinha, which basically do cataract removal to subjects which didn't have visual experiences or have very, very limited just light perception in the age of 7, 13, and 29. And they basically test them for visual parsing. And what is quite amazing is that even 1 or 2 or 3 months, actually it's not amazing, they said it's expected. What is amazing is what's coming in a second. But even after 1 to 3 months, by seeing all the time, basically receiving this visual information and interacting with the environment, because they don't have any other option besides when they're asleep, of course, they fail miserably in visual parsing. So they can say this is 2 objects, but in all these instances, for example, here, all the 3 subjects would say this is 3 objects by the different luminance, and they would find it extremely difficult to build the 3D information. Now, can we train our subjects to learn to do visual parsing using this type of approaches? So this is what we aim to do in this project. So what we do is basically to download exactly the same stimuli and test them using the voice following the training. So again, 70 hours of training. And the cool thing is that 70 hours, and in many cases even more, is enough for the subject to being able to do all these visual parsing abilities. In all the cases, surpass greatly what the subject's been doing after 3 months. Now, the amazing thing, which challenges to some extent the issue of critical periods for the ventral stream, because the dorsal stream recovers much more quickly, is that after a year, in some cases, they start to develop these abilities. Not perfect, but some of the subjects starts to get into this, but this is comparable to what our subject did after 70 hours. And in many cases, like in this 3D, the subjects are much weaker. So in a way, we can use auditory sensory substitution much quicker in order to get the notion of visual parsing. And then what we try to do next, this is a project led by Lior Reich from the lab, is to try to see whether we can use this local and understanding of the environment to do something which is very important. Another thing that is very important in vision, not just parsing, but doing a rotation and try to judge the orientation of objects. And so we were having simple geometrical shape and houses in different levels of complexity. We trained them on one set and tested them on a completely different set. And what is pretty amazing is that they were able to do this on both geometrical shape and very complex houses, to be this complex or line drawing, et cetera, et cetera. So in a way, we can put a foot in the door on this, and I'm not claiming that this is by creating a holistic vision like we have, but it's finding this cognitive experience and statistics to be able to do quite complex visual experiences. Now, the second question we ask using this is what happens in the visual cortex without visual experience. So in a way, we're trying to look at what are the innate constraints together with this cognitive and training and experience on what happens in the visual cortex. And later, we not only ask what activates the visual cortex, but whether functional specialization can develop over hours and tens of hours, okay? And then we might connect it to invasive stimulation. Now, the starting point of this is, as was mentioned very, very briefly, is that we previously found if we don't train with sensory substitution, is congenitally blind recruit the visual cortex massively. They recruit the entire visual cortex in the left hemisphere for language and memory functions. This was a 203 paper. But what is interesting is that it's also, early visual cortex also correlates with how much superior performance they would have. And this is with various memory tasks. And you can see here the results from sighted and from congenitally blind. So in a way, they take massive parts of the left visual cortex to process this. But actually, the picture was, and this is a difference. This is the work with Zohari from the PhD. What was more interesting is that what we found is actually, in a way, an inverted hierarchy of the cortex. And if we contrast retrieving words, abstract words from memory, or reading them with Braille, or doing tactile perception versus tactile memory, we start splitting this homogeneous activation and massive recruitment of all the cortex, and there is starts to emerge the vision of labor of some areas are activated, the posterior part for the memory and the other for the perception. That might be tactile or auditory. So the question whether, and the second starting point of this is the finding that actually even in the sighted brain, we can find recruitment of object recognition centers for tactile object recognition, and it seems to be much less significant than visual imagery, but here you basically have the constraints that maybe you would still imply visual imagery, so this is how we started to work on the blind. And one recent result is that actually if you look at LOC bilaterally, you would see that the activation is bilateral, just like in vision, and it shows preference for objects both in sighted and congenitally blind versus controls. So the question is what's going on when they start using these sensory substitutions? Can it further specialize, or the picture is... so basically what happens when it's going on, and usually you see a selectivity picture. So here we just look at the activation versus baseline and pull out any object stimulation or reading. And what you see here is that there is activation both in the auditory cortex and in the visual cortex. I will get into a finer resolution of this and a more careful design. This is just to highlight what's going on. So it seems that actually from some of the things that were raised here is that it's not the visual cortex that's recruited. It seems like both the auditory and the visual system is activating massively, and there seems to be some order. So if you repeat it many times, since sensory substitution is so slow, you can start looking at the dynamics of it. So it tries to see where it starts, and it always starts with a brief activation of the auditory system, which is continuous, and then the peaks travels using both latency mapping or phase analysis into the visual system. But then what is really interesting is that if we can start using this training to differentiate between various functions and tasks, we start getting, first of all, much cleaner activation. So for example, if we look here on object recognition versus scrambled objects, or if we look into reading versus face processing, houses processing, etc., all these very complex categories that I will show you in a second, the blind can do this categorization, we start getting activation in the visual waveform. So let's dive into a little bit of the details of it. So first of all, as I mentioned, LOC, the Visual Object Recognition Center, can show object selectivity to tactile, as I showed you in sighted subject and in blind, and also in the auditory modality using sensory substitution. But the key point here is that this was happening only if the auditory information contained geometrical shape. So this basically leaves us with two. So for example, if, and this was true in sighted and blind, but if we basically let them do association on the same physical stimulation, and I will show you a couple of evidence about using the same physical stimulation, but doing different tasks. So in this case, the task was to do association on the sounds. So we learned that this is a horse. Without knowing what is sensory substitution, you would not recruit the LOC. Okay? And one very interesting anecdotal, and this is the famous PF. Okay, the movies are not, I take them time. But basically, the bottom line of this study by Merabet and colleague is that we basically send them the activation of PET using object recognition, and then they did recognition of objects before and after TMS, and were able to causally show that, at least in this anecdotal case, the images of the object starts to be incomprehensive. In some cases, she can't even say the objects are there. So this is very anecdotal, but it shows that it might be that this activation is given rise or participating in the network that is doing this type of task, but this needs to be tested more seriously in the future. maybe using TDCS, TMS, and other approaches. The second thing we wanted to look is whether we start getting and then later strengthening basic division of labor. So you heard a little bit about, for example, recruitment of MT for moving stimuli. So in this project led by Elaf, Trial, and me, what we wanted to do is to keep the physical stimulation, again, exactly the same, but only change the task of the subjects. One time they get exactly the same stimulation, but they need to say something about the shape, okay? And then if it's about the curvature of the shapes, and the second, they need to ignore the shapes and say something about the locations, and all in the same experiment. And what is really interesting is that in the ITS and the precuneus, both in the sighted and in the congenitally blind, there was selective activation for shape and for location. There was a very interesting pattern in the intermediate areas of the retinotopic areas, but I'm not going to get into it. So it's not that all the cortex is always showing this. It's actually showing some deactivations in the sighted. But what is really cool is that as the training progress, then there is further recruitment of the ventral stream for the shape task, and further recruitment and strengthening of the activation. So if you compare post versus long training versus short training for the location versus shape, and then for the shape, you get selective recruitment of this. The next thing we wanted to look at is to try to look in a similar way to what Laurent showed you some results. Laurent Renier, interesting results about faces. Our first pick on it was to look into reading and into visual words, which have a very selective pattern of activation in the sighted versus many visual modalities, and was also triggered by a previous experiment we did with braille reading, and I will show you this in a second. So basically, in our experiment after the training, the subjects were able to categorize successfully the stimulation they would get. So they can say this is a face, this is a house, this is a body, this is an object, etc., etc. And all much significant than a chance level. But now, what happened when we look at their brain and look for selectivity? So first of all, in the sighted, if you do the letters and this type of stimuli, let's say versus all of these categories, so this is a very strong demand. You want it to be more significant and above baseline to faces, to houses, etc., etc. You will get very selective activation in the left hemisphere for this in the sighted. But what we were really struck when we look at the same in the congenitally blind, we're doing the same thing, we got the same level of selectivity, even a bit more. And this was actually more than we saw for any other categories. It's very interesting that it's another maybe parallel between reading and sensory substitution. And reading using sensory substitution is in a way very selective into recruiting the visual cortex, and you see the rest is very clean. Again, if you would look at versus baseline, you would get this early responses in the auditory cortex, which is maintained, and then the activation would go, as I will show you in a second. Just to stress how strong this result, even if we compare each one of these letter versus each one of the other categories, we still get overlap on all of these cases, and also overlap in the single subject case. And this was very interesting because actually I think the talk shows a lot of parallels between using the tongue display that Maurice showed you, using natural touch and using auditory to visual to auditory sensory substitutions. And in the case of reading, this is converged from all this, and for object recognition from all these angles. So for example, this is a previous study led by Lior, which look at the peaks of activation of braille. So actually, if you look at braille activation versus a homogeneous pattern, you would get activation in V1, just like reported by Sadato and colleagues in 96, but this is actually not the peak across the entire brain. This is much weaker than the activation in the visual word form. It was just not, it was more exciting and significant to look at V1 and look at this activation, but actually the peaks of the group are located in the visual word form. But what was really interesting is that even if you look at the single subject and look at sighted reading by sight or blind reading by braille, you would get very, very similar pattern. So sighted by vision, congenitally blind reading by braille, recruit the ventral stream, and maybe it's all about the task and the computation. So here the computation would be maybe to connect symbols and phonemes and symbols and start building these word entities. And this actually gave us rise to a very interesting study by a single case, but not PF, of a really interesting subject, which was a proficient braille reader. So she knows how to read braille, but she don't know the Hebrew alphabet. Some blind would have some familiarity with the alphabet of the sighted. She didn't have any. So in the training, we made sure to train her only on non-Hebrew alphabet, all the rest of the stimuli. And then we scanned her brain using letters that we are going to teach her in Hebrew and in Braille, and letters using the sensory substitution, which she's not going to learn. Okay? Is it clear? Okay, so for example, in this case, she will learn W, but she won't learn A. And in the visual word form area, this is the Holberg analysis, you would see that before the training, so she's already proficient with the voice, but before the training, she has activation for Braille, but not for all the other conditions, not for the homogeneous and not for the letters that are not going to be taught. But after 2 hours of training, she's been scanned again, and she starts having significant activations also for the sensory. So this is another generalization across the senses. And the last piece of evidence before we'll go into the color results is this study by Nadine Sigalov, in which we basically do a letter by letter and then a word reading, and then she would hear the same word semantically or a different word, or a scrambling of the same thing and then hear the word. And what is really interesting is that, first of all, there is a drop in the activation when she hears the word and she's not reading. I'm not going to show you this. But there is also selective activation that starts to build up, not in A1, but, and actually it's even a little bit the opposite for the scramble. It starts to build up as we go into the visual word form and the parietal letter-by-letter onset. So there is initial activation in the auditory cortex again, then actually it goes to more early visual cortex, and we're still trying to understand this. We don't. We have some ideas, and then it goes to the visual word form area. So the visual and parietal letter-by-letter written network, including the visual word form, appears to relate to the task of linking letter shapes and phonemes, regardless of sensory input, visual experience, age of learning to the script. So I remind you, this subject that learned in a late age, and the visual cortex. And just to mention another results from the Pascal-Leone group is that they had a case of occipital stroke that caused a blind to lose its ability to read Braille. Okay? Again, anecdotal and single case, but interesting. And this also, we showed it for object recognition, for ventral dorsal, and can all be enhanced by experience and training. So this concludes this part of the talk. Another effort that we are currently having in the lab, led by currently by Sami Aboud, which is here, and Shachar Meindenbaum, is to try and create a sensory substitution that we can control and give additional information for the blind subjects. And two things we felt are really missing, and we can improvise something really nice and try to improve it with having all the controls over it, and then do some neuroscience with it, and also try to make it available to blind individuals. Is first of all, the eye is depth and color. This is two things which are missing from it's very evident that they are missing directly. So basically, it's a very, very simple 1 point or 2 point. You can experience it here in the demo, and it gives you up to 5 meters of estimation of the distance of things. So it gives you depth to the objects. You can also try to combine it with the camera and get both the depth and the image, etc., etc. And blind subject can even differentiate things which are difficult for in vision, like illusion, etc. I won't elaborate on this too much. But another thing which is useful using these devices is that you can actually give exactly the same information using virtual environments and then train the subject or teach them novel environments and so on and so forth. And this goes into this image which emphasizes that one of the main limitations of blind individuals is that they perceive space in a big amount of the time as a very small relative to the sighted. You can see here that the blind is focused around their closed space, and then the sighted look around. And one of the first things that the subjects told us is that it's open for them rooms or environments very quickly when using it. The second is the EYEMUSIC that is also going to be here in the demo. And basically it's adding two features. One is trying to use musical scales instead of just pitch, and the musical scales can, in principle, in the future, you can vary the different scales, etc., etc., and use scales that give harmonics that in many different combinations can still give you something that sounds okay or good. And I would show you a couple of stimuli. And then we also add, we run so there is a lower resolution, and you can play here with different resolution and pleasantness, increased resolution, decreased pleasantness, etc. Then we run color clustering, and then we scan the image just like in the voice, and basically have association to various colors. So just to get, so basically in this case, for example, Chamutal would scan an image, get where it's located, differentiate the cluster of apple from the clusters of the green, connect it to her body reference frame, and do an action on it. And she can do it to various objects. In this case, she would each time try to locate the Sprite bottle and do this clustering and so on and so forth. Yeah, so then you can reshuffle. You can use this to combine both image and color for science, etc. So just to give you a gist of it, for those of you who won't be in the demo, can you increase the volume? A little bit lower. So this would be human voices for in all this case for representing the white. And it would go down, lower, and lower. Now a vertical line would be sorry. So stairs would be vocals going down. A vertical line would be much briefer and more dirty. Gap and the pure line. Okay. Okay, and now you can start reading in. And then we can add colors. So for example, so it would have the same geometry, but now the timbres would sound different. And we can also try and draw various things like a hill and a sun, a different timbre, and a lake, and so on and so forth. You already saw this. I'm going to show you and finish up with basically showing two additional, one behavioral, that Derek will comment and I'm sure, like as a good philosopher, will crash into dust, because this is the paper I sent him. And then we'll have another one, which is a very recent experiment we are very excited by. So basically, the idea in this experiment was to see whether they can use color cues to locate them. So first of all, they can do it quite accurately, both in vision and the sensory substitution, to have the sounds to guide them. But then the interesting experiment was the following experiments. In this case, they would have a joystick that they can't see. They were blindfold. This is sighted individuals. And they need to go into one target or a different target, okay? And they practice in it and get very good at it. And then, and they can do it with vision or with the heard sensory substitution sound. But then at some point, you will start getting something that is known in the literature already, that if you create some perturbation, so they would go here, but the cursor would go here instead, they would just assign it to, they made a mistake, or it's becoming more difficult, and they would start implicitly correct for this perturbation, okay? And now what is interesting is that if we would have this perturbation coming only in the visual modality, and then we tested both on the visual and the sensory substitution auditory randomly, then we can have two predictions. One of them, since this is something implicit, and there is a vast majority about subject being not aware of this correction, and we run also some questionnaires, etc., then we can expect that there would be a correction in the visual, but it would not transfer into the auditory, because here there was no perturbation and no reason to do it. The other option is that this will be transferred, okay, and they would start correcting also the sensory substitution case, or there is no need, and this is exactly what happened, okay? So they start to correct the visual trials, but they also do the same and transfer this into the auditory trials if they would be removed. So there is an implicit cross-modal transfer and adaptation between vision and audition space representation. The last project I'm going to show you and then recap with saying a few words about sight restorations effort is this experiment by Sami. And the experiment is trying to take the issue of task activation with having exactly the same physical stimulation using the EYEMUSIC and basically using exactly the same type of stimulation and trying to see what's going on in color. So the stimuli were these three stimuli. Basically, you would have stimuli that you can make a task of trying to say something about the color, okay, or find a target above the color. You can say something about them being letters, I, X, or V, or you can look for a target which is a number, okay, so a Roman number. So the physical stimulation using the EYEMUSIC is exactly the same each time, just the task that they are performing is different. And first of all, and then we scan the brain before training and after training with the sensories, with the EYEMUSIC. And basically what we see is that post-training for the color versus all, there is a recruitment of the ventral stream, okay? It's not specific only to V4, as we might expect some hypothesis might be, but there is a specific recruitment again of the ventral visual stream in addition to the auditory cortex in the pulse. But then what is really, really cool is that if you look on the specific post-training effect versus pre-training, and also look for the selectivity for colors versus judgment of them being a letter or a number, you would get overlap in these ventral retinotopic areas. So this is preliminary. We're still having the last steps of data analysis, but it suggests that even something which, and just to stress again, this is for subjects that are congenitally blind. They never had an experience of color. But still, the area they recruit next after processing it in the auditory cortex would be the retinotopic areas in the ventral stream. Okay? So the final comment I'm going to make is to ask how can we assist visual cortex to see again, and here I think it's become very interesting also philosophically to look at the differences using invasive versus non-invasive approach. So as I mentioned here, this is, for example, the Argos 2 device, which is containing 60 electrodes, and this is a device that is approved for chronic implementation. There is patients in the US and in Europe. And what is interesting is that when you activate this device and stimulate the ganglion cells, okay, even after years of blindness, you would get immediately a flash of light, okay? And by the way, it's really interesting. It's not trivial, and we talked a lot about TMS. In TMS, if you stimulate the visual cortex, you would get visual phosphines in some of the cases and in some locations, but that's basically the only visual sensation you can trigger using TMS. So anyway, here it's much more consistent, and the subject would report immediately the quality of seeing light when they stimulate the neurons in the retina, even after years of blindness. But the thing is that the performance is really, really poor, both in the beginning and even after, again, months and even a year. And there is a huge variation between the subjects. And just to give you the gist of it, you saw how fast it will be for you to read the word heal using a sensory substitution or a different word. This can be happening only in a single letter or two letters in half of the subjects, and it will take them a lot of time to process it, a minute, 2, 3, until they would be able to do it. So actually, maybe what we can do is to combine Maurice talks and my talk and other groups, Laurent's data and some other groups, and try to build something which try to enjoy the best of all this world and do this type of rehabilitation of the brain. So you would have the camera capturing the information, stimulated the neurons and get the qualia. You would have the auditory substitution give you the same resolution and try to provide explanatory signal that we showed you can teach very, very quickly, much quicker than the prosthesis itself, although it contains the qualia, and this is not containing the qualia. And then we can increase the resolution using visual to auditory sensory substitution, but we can, and this is just a study trying to see how far we can push the resolution, the theoretical resolution that you can actually, by doing a separated Snellen experiment, and you can see that you can, in principle, have thousands of pixels. It doesn't say that you can use them. You need to learn how to use them to combine them. But then we can also add tactile devices like the cane sensors or the tactile matrices like the tongue display or other displays to add visual flow, to have movement that are much more better from the other senses. So in a way, we can create something that would have the two different basically approaches of trying to reconstruct something in the periphery and trying to use all this cognitive and experience and statistics of the brain and try to bring them together to be able to restore as much as possible vision. So I would like to thank this is a collaborative effort by the students, and I mentioned the main students that I was presenting the work, and some of the collaborators, and to thank you for your attention. We can finish with this inversion effect on the Mona Lisa. And thank you, slide. Okay. So. Do we need to switch this? He'll do it.
really cool building. Thanks, Amir, for the talk. I didn't know of Amir or his work about a month ago, so it's been an instructive month, and he's been writing the talk for the last few days. And as a philosopher, that frightens the heck out of me. There might be a couple of philosophers in the room who read a talk in the couple days leading up to it. I'm certainly not one of them. Yeah. Oh, that's fine. That presumes I know how to use it. I know what the arrows do on my computer. So the commentary isn't based on the talk, which I just heard, which is really, really good. Amir's doing some cool stuff. The commentary is based on 3 papers that Amir sent me a couple weeks ago. See, I don't know how to use it. Let's use that. So one of the papers was a quick summary of general issues surrounding his EYEMUSIC tool and visual auditory SSDs generally. One of them was about this transference of learned motor skills across sensory modalities. The third one was about structural integrity and multisensory activation of specific areas of the visual cortex, including the visual word form area, which Amir had a couple slides on. And that one in particular is quite cool because you have this kind of not just the areas of the visual cortex being accessed or utilized by other sensory systems, but the actual functional integrity of some areas being preserved across sighted and blind people, like in the visual word form area. The commentary itself is about 30 minutes long. Here's a third of it. It concerns the second thing, the transference of learned motor skills across sensory modality. I decided to focus on that. Okay. Amir had a couple slides on it. The main idea is a simple one, at least to say, that a motor skill learned through visual perception can be employed in response to auditory perception. This is a kind of transference, and he was utilizing his EYEMUSIC device to assist with that. Okay. At the beginning of the paper, they say, Amir and his colleagues, that's the they, a priori, and I thought, he's a philosopher at heart. There's no reason to assume that this would occur. On a weak reading, this is just to set up what we would expect, which is, I'm a scientist, let's go get the data and figure out what's going to happen. But on a slightly stronger reading, this expresses an expectation, a hypothesis that you're going to test, right? And you might initially think the hypothesis is quite plausible if you're concerned with motor skills involving traditionally modality-specific features of targets. But if you're using motor skills involving non-modality-specific features of objects, you might actually come up with a different hypothesis. But regardless of your hypothesis, the experiment, as he described it quickly, involves a subject having a joystick that they can move from an origin to a target. Right? And this notion of feedback is crucial to it. Amir didn't mention it, but I'll mention it for you because it's pretty intuitive, straightforward. So we have a visual case. A visual stimulus is like a computer screen, and the cursor might be a dot at the origin of the screen, say in the middle, right at the bottom, and the target might be a dot some other place on the screen, and you can move this joystick, and the joystick moves the cursor around, and your goal is to move the cursor from its origin to the target spot. And feedback is there, this visual feedback, because as you move the joystick, you can see the cursor moving. Right? In the auditory case, the kinds of soundscapes that we got clips of just there, you'd have a beep at the origin. So if it's at the bottom in the middle, it would occur in the temporally at the middle of one of these soundscapes. And if it's at the bottom, it would be lower in pitch. And you have some target location, which is, say if it's up here, it would occur closer to the beginning of the soundscape and higher in pitch. Right? And the joystick, well, you can move the joystick to try and make the origin beep get to the location of the target beep. But there's obviously no auditory feedback going on as you move the joystick as to where that's going to go. So you start making guesses. And you train this and you get good at it. Right? Then you introduce this rotation effect or perturbation effect during testing. in the visual case, say, where you have to move the joystick now in a more pronounced way in order to achieve the same effects that were going on in training. And you're getting this visual feedback, so you can do some corrections for it and start initiating this learned behavior. Then you throw people in the auditory case, and the feedback's gone, so you want to see if the learned perturbation effect, if the learned behaviors to counteract the perturbation, if they carry over into the auditory case. And in fact, they do, and they do quite nicely. So I think that's a cool, interesting result. I'll say two things about it. One of them is some further experiments that they might wish to perform. And this turns out to be hopefully helpful, but if not helpful, at least a good thing to be trying to do, because Amir tells me this is the first bit of results that they've ever done of this sort. Right? So it's the beginning of their research program on this. So maybe they want some ideas. The second thing I'll say is a little bit more philosophical. Okay, so you might want to just do the reverse. Test to see if this this learned motor skill can go not just from vision to audition, but from audition back to vision. It may be the case that you have a stronger effect one way than the other. Right? This would require introducing feedback to the auditory component and removing feedback from the visual component. The latter isn't tough to do. Right? If you have a visual screen and the dot at the origin and the dot at the target, you just make it so that the joystick will invisibly move right, the origin dot toward the target if you move it in the right place, and just don't have a visual cue as to what's going on. Introducing feedback in the auditory case is a little bit more complicated if you're thinking in terms of the soundscapes. Right? And in fact, I would suggest you should leave the EYEMUSIC kind of soundscapes if you want to introduce that. I don't know if Laurent's thing would work or not, but if you're able to generate sounds perceived in a two-dimensional plane in front of you, for example, you could have your origin sound down here, and you could have a target up here, and you could have the origin sound move and hear the movement, right, and try and move it toward the target. And then you'd introduce feedback, right? Continual feedback. That's one way of doing it. There's probably lots of other ways of doing it. And you could then train subjects on both. In effect, the visual component, right, the looking at the screen, is kind of serving as an SSD for the auditory in this case, although it's a loose use of that term. But you could then introduce the perturbations, right, the joystick perturbations, see if in the auditory case people are learning and counteracting for these perturbations, and switch them to the visual and see if those carry over. Look at the difference between the two. Of course, once you've got this going, you've then got four kinds of scenarios. You've got a visual case with feedback and a visual case without feedback, auditory case with feedback and an auditory case without feedback, and that allows you to do some modality-specific tests. Right? You could look at auditory with and without feedback and see if in the feedback cases, they start learning how to counteract these perturbations, and if that carries over when you remove the feedback, and similarly for the visual. And what's nice about thinking about this is one of Amir's other really cool results, the stuff about the visual word form area, maintaining its functional integrity for accesses from different modalities. Right? He's really interested in finding non-modally specific areas of the brain and non-modally specific functions in the brain. And it looks like if you get visual to auditory transference of motor skills, that's some evidence that the motor skills that you're learning aren't modally specific. But if you compare that with all this kind of stuff, you might get a better picture of how that works. Right? It may be the case that if you do within modality tests, the transference across feedback and non-feedback cases is roughly the same as it is across modality, in which case it looks like the transference power is completely non-modally specific. Or it might be the case that within modality tests, the transference is stronger than across modality, in which case Amir can start, in this case, answering this question, well, how much of the transference of the motor skills is modally specific? Here's how much it is, right? And you could do this with other modalities too. So there's some suggestions about where he might want to go and why they might be interesting and fit into some of the other work he's been, some of the ways of thinking about the brain that has come from his other work. The second point I want to make, this a little bit more philosophical one, is that this notion of transference is quite familiar to us. And here's a quote from the paper, which is right at the end, near the end, I think, or it's in the paper anyways, from Amir and his colleagues. This is the first demonstration, to the best of our knowledge, of transfer between the visual sense and the visual to auditory SSD. Okay? If you think for a moment about behavioral associations, old familiar ones, behavioral response to stimulation of one modality has been transferred to behavioral responses to stimulation of another modality. That's not a new idea. That goes back to the beginning of behaviorism. And if you look back at the quote, someone might say, yeah, but that's a behavioral response as opposed to a behavioral motor skill. And I'm interested in motor skills. And of course, you could easily generalize that to motor skills, and I'm sure there's lots of experiments that have done that. Well, then you could say in response, this involves going from olfaction to audition, and I'm really interested in vision to audition, and I'm sure there's other cases that can already exist that involve cross-modally going from vision to audition. You might still respond by looking at the quote, yeah, but none of these involve visual to auditory SSDs. Right? And there's two things that we should keep in mind if we consider that. One of them is that you may think the main issue isn't about the use of SSDs. There's, of course, interesting questions about the uses of SSDs, and this might be one use to which they could be put, but the main underlying issue is whether or not we can do transference of motor skills across modalities. But you could also think, in response to an objection like this, that in some of these classic behavioral association tests, maybe you do have a primitive kind of SSD. So you have a form of information like there's food there, which normally comes through olfaction, and now is being read into a stimulus that's auditory. Kind of looks like a primitive kind of sensory substitution device. You could object some more and say that this isn't the right kind of transference, and I think there's ways to respond to that too. But I guess the overall point is just to point out that, or is just to suggest that I like the result, and I think there's lots of other things we can do with it. And rather than think of it as a standalone thing, right, a first demonstration, we should think of it as belonging to extending on this long and illustrious lineage of data that we already all know and love. Thank you.
All the points you made are very good, and thanking also for writing our next grant, so that's excellent. I think, but in relation to your more important point about trying to connect it to previous work and see how much this is trivial or not. So first of all, I think the connection to the work of Pavlov, etc., is really, really interesting, and it sounds very straightforward. But what I want to emphasize here is that one thing that might be different fundamentally between the two cases is that here you have a very direct mapping of one stimulus to the other stimulus. While in the case of this implicit learning and movement, you have some perturbation. The perturbation was 30 degrees. It was small enough, according to literature and all the questionnaires that we filled in, to be implicit in a way. So the subjects would say, I don't know, it's a little bit more difficult to me if you ask them, or say, but they would never realize that you tricked them and you did some of the perturbations. And then slowly they would start implicitly to correct it. And the fact that a transformation that is adaptive, and then in the same way it's transferable and adaptive in the same way to another modality implicitly without, presumably, at least it seems that it's fitting the literature and the questionnaire, is, I think, a bit more fundamental than just saying, okay, this is one thing triggered by the other, and it's a very strict way of associations. So this is maybe...
Yeah, no, I'm certainly happy to concede the point. It's not that the analogy is strict, right? It's that there's the roots of this way of thinking of things. And in the SSD case, we've got these mapping relationships between the visual and the auditory that obviously isn't there with something like a bell.
Yeah. So my question is whether you found shape-selective activations in the lateral occipital complex for novel objects or just for familiar objects that the subjects have been trained on.
No, that's a fantastic question. So, first of all, there is a follow-up on the 2001 work, beautiful work by James, which and colleagues showing that it's active for abstract shapes, and even more than this, there is a priming effect. So, if you prime in one modality, you would get a transfer to the other in this sense. So, it seems to generalize. Also to abstract shapes. And basically this gives me to elaborate a little bit because I think I rushed through some of the data. So the idea would be, and here I think it's very interesting to discuss, there is two options. One is that one option is that this cortex and the connected networks are building 2D or 3D geometrical combination of the features and learn how to do it. So in a way, it's a very perceptual thing. And the second option is that that might fit more with the notion that Kevin was raising, is that by doing all this interaction on object shapes and combining this bottom up with all the things that we know about parsing, about building the curvature, etc., we start to build this selectivity.
Thanks very much.
So I was really interested in the idea of representing color with sensory substitution devices. And I noticed that you represented 5 colors with 5 different instruments. And I was wondering if you've experimented with a more continuous mode of representing them. So I know that voice, for instance, represents brightness through volume. And I was wondering if that's been tried with color or something that's more continuous, like volume has been tried.
Yeah, so I would mention 3 pieces of lines of work. First of all, Jamie's Words Lab is doing very interesting work in looking at this type of more continuous representation. We are doing some of this effort to look at what happened when we try to do it continuously, but this is more of a point. This would be easier to do on a point basis. If you want to combine both some level of representation of the 2D array in a more holistic way, it's a bit more challenging. But if you try to do it more locally, then you can play with it. And there is there was mentioned the first cyborg that basically try to have this continuous pitch with colors, etc. So we did some work along this line. But our approach was to try and use clustering and figure ground and to get something that is more consistent, that would allow us, with the previous work we did with the voice, and would allow us to introduce the concept of color and figure ground and etc. in this way, but also to try and use vocals and combination of different chords, etc., to start and play with it in the future in a more array concept. It's definitely not the only way to go, and there might be for sure there's going to be other interesting ways to represent colors, and there's other groups that are play with this concept.
Can I make a quick comment on that too? There might be some advantages. Continuous might be great to explore too, but there might be some advantages to having just a small number of categories. If you have a small number, you might think one of the reasons we have color categories in our experience at all, instead of just a strict continuum, is to help us chunk things out so that we can distinguish between objects or their colors and track them right more easily than if it was just continuous. And similarly, if you transfer that sort of chunking over into the auditory case, especially if you map it with timbre as he does, if you only have 2 or 3 different timbres, a trumpet, a saxophone, and a piano, and if they're all happening simultaneously, it's not that hard to pull them apart. If you had something continuous, it's quite a bit harder to pull it apart. And as you go across scans, it's easy to re-identify the trumpet, and you can track where it is. But if you had something more continuous, it might be a little bit more difficult. So there might be practical advantages to chunking it in the way he's doing it.
So your research shows that letters are special, but I'm not quite sure that they're necessarily special for the way you describe. So you say they're special because they link to sounds, but if you take a cup, you can look at that and link it to a sound, so its name as a cup. I think one of the reasons why a letter is different is that they have particular properties. So the shape is quite invariant. So if I turn the cup around, it's still called a cup. If I turn the letter B around, it becomes a D. If I turn the letter E around, it becomes nothing. It's wrong. So letters have particular properties, and it's not just that they link to things that can be named.
Yeah, I think I missed. I didn't. The way I was referring to why I said letters are special is that when we look at the various categories and the various selectivities in the cortex, we got some other selectivities like to objects, etc. But the letter selectivity, both in the case of the Braille and the case of comparing it to all other, and the cleanness of this relatively result from brain images, it looks like it was the most clean specialization that there was, at least in our experience, by just looking at the brain, not beyond this.
But why?
That's a good question. It might be that it's a bit more multisensory in essence. It might be the connectivity there allows this to emerge. It might be this characteristics that you mentioned, although it's definitely not the only, and you can have variances of reading opposite and etc. And you can still do it. We have Yemenites that read in Israel that reads perfectly. They are trained. I don't think they are special in general, but it seems like they were giving emergence to a more specific and clean result relative to other things that we saw. Just observation, nothing more than this.
Just on that, before I ask the question I wanted to ask, numerals are special also, and in a different area. So there's some new work by Joseph Parvizi in Stanford, who does direct cortical stimulation, and it's not the Hans visual form area, it's another area, and it's in the temporal region. It's just here, and it's the same in all the patients that he looks at, despite you'd imagine individual differences. They seem special. So maybe it's worth looking at that too, just as a way of testing on numerals. But I wanted, taking a long run up at this question, I didn't see quite the analogy with Pavlov, because there you've got two modalities you have access to and you're making them combine. I took your point to be you've got a modality you don't have access to, and through the SSD you have to combine it with the unexperienced modality, but you recruit another modality which gives support. This is the idea of our experience usually being multisensory. So you bring in something else and give it support, and then try to use those kind of bindings to help you give more texture dimension to the SSD about the lost modality, about vision. But now I want to ask whether what you said is actually a philosophical challenge to Kevin O'Regan, because Kevin was talking about exploiting the very sensory motor capacities that are supposed to identify that type of sensation. But from your stuff on music and color, you didn't need to recruit a modality that's usually there and usually supportive and usually part of the total picture of multisensory integration. You can recruit something that isn't usually there, something artificial like the musical scales, and bring that in. So it looks as though you're saying, as long as you can get multisensory support, it doesn't have to be the very same contingencies that are usually at work in normal subjects, that you can use any support you can get, as it were, to build some new sensory motor contingencies that might get you to have the SSD work better.
Well, that's an interesting point, but the problem is that I'm a neuroscientist and not a philosopher. So my answer to this would be that maybe the type of recruitments we got, both in the case of the ventral dorsal, like the beautiful DTI results Maurice showed us, and maybe other predisposition, we have some innate predisposition that using the congenitally blind enable us to tap into these contingencies, and it might be that it's really difficult to think about it, how exactly, but it might be that the ventral stream has more innate tendencies to be recruited by shape and the dorsal for location and action. That's more easy to try and think about what is this innate constraints might do to push the system to recruit in after you have the initial analysis of the frequencies and combine them to transfer it to the brain transfer it to the visual system. And it might be that still, even though they never experience color, they have some innate predisposition in the ventral stream and less in other places in the brain.
So that was the basis of the question, whether you want to test and see whether it's about the innate correspondences, tendencies, whether there can be some artificial ones and they work just fine.
Yeah. I think another thing I want to emphasize, which actually goes in the direction of combining this notion with sensory motor and with, is that physical stimulation was the same all the time. It's the task and the motor. It doesn't have to be, in my view, only motor, but the concept of having a task, being it perceptual or more perceptual weighted, or for sure any sensory motor would enhance this or be independent of this, would tap into these resources that we have innately. And then we can, like in the single case example or in a very elaborate training, sculpture, modify, or change completely. And this is very interesting to look in the future, how much this specialization can be flexible, how much it's relate directly to behavior, how much it's can improve or not, how much stimulating can enhance or suppress, etc.
We have a comment.
Yes. Thank you, Amir, for this very nice talk once again. And as I told you, I was very pleased to present before you this time. I have a question about EYEMUSIC. So as you mentioned it also, color should be a very abstract concept for the blind. How did you explain to them the different color? What is that?
Yeah, so it's first of all, they have knowledge about that there are colors in the world, and it's basically associations. So they say, okay, this is blue. So for example, in the case of the bottles of the Sprite and Coke, they need to remember that Coke are red and Sprite are green, and learn these associations. But it's not more than deep than this. But I do want to mention, for example, that there are cases of blind be able, like Esref Armagan, to draw very vividly and use colors and concepts and even shades and even light without having the experiences. But what exactly do they experience? I think that might be
this is
philosophical and
it's hard to me to understand if it can be meaningful for them. It seems very arbitrary, but a good argument is that it recruits the ventral pathway, so maybe they...
I think the most relevant is that if you, for example, if you want to reach for something and it has now relevance to segregate it from the environment, this is something meaningful. And you didn't have this input, this information before. Now you have it. So this is meaningful. And now if you want to start using these notions in the world to try and work upon the world, then you have another dimension to act upon it, which actually is a very important in vision. We know, for example, parsing is extremely dependent on using colors. So it's actually be very helpful for fair ground, can be helpful for the building objects, for et cetera, for a lot of visual functions. So even though they don't have any experience of it before, they can still learn to use it, I think, in the real life.
Thank you.
Fiona.
Can I make a comment on that one? I just would like to add an anecdote of, we have two blind subjects we have been studying very well, and they lived both together, and we once went to their home to see how they were living. And actually we asked them also about color, and then they explained that for them, although they could not perceive color, color for them was extremely important, that they had among them, they had long discussions about which color they would paint their living room and how it would actually match the color of the wall paints, how it would match with the color of the furniture. Because cognitively, of course, they learn that these and these color matches. So for them also, I mean, the colors they have certain meaning, which is transmitted in a cognitive manner.
I think it's a fantastic point, and it's also might highlight another use of sensory substitution, and this is to make the social interaction with the sighted society more easy or more direct or more access to them. So this is a really fantastic example. And they use also semantics many times of visual like, so it's a well taken point.
Amir, you started off your talk by saying that there can be dramatic shifts of experience in virtue of cognition, and you had this nice FedEx example. And I thought that you might go on to say something about, I thought that was going to be a prelude to saying that there are shifts in perception of your subjects, either a dramatic shift in their auditory experience, or a shift because they come to have visual experience, or a shift because they come to have an amodal experience. But you didn't actually say anything about that. So I want to ask you to comment on two things. First of all, what do your subjects, particularly the subjects that have had the most training, what do they say about their experience, and what's your sort of considered overall opinion on the issue of how their experience changes?
Yeah, so this is a really tough one because, first of all, we didn't do it systematically. It was not part of our agenda, especially because due to imaging reason, and you can wait out, for me, it's an amazing quest to look at what happens in the brain, how it's changed, and what's... So for me, this is a really fun scientific and general experience. So in a way to look how the dynamics of the change and the reorganization and the organization and what's stable and what not was important. So this is why we selected congenitally blind versus late blind. The second thing is that actually with the congenitally blind, there was a lot of very interesting things that we didn't test it systematically, but were really, really interesting and a very important part of the training. So just to give you a very simple example, for example, when you get closer, you get the objects closer to you or farther away, or when you move your head to the right or to the left, the notion that the object moves or changing the size is very strange to them in the beginning. And they don't know how to relate to it, to their motor action. And then they need to learn that when there is a cross and they get closer to it, it gets bigger. And it's not happening in touch. You get it closer or farther away, it remains the same size. And there is a lot of these things that they need cognitively to learn, and they start to use it. So in this sense, dramatic things change in them, but I can characterize it more in the experiential level, and we didn't systematically tested.
Thank you for a very interesting talk. I was quite interested in the way that you said they developed the ability to do effectively visual parsing, and perhaps they didn't have that experience before. But surely in the auditory domain, when we parse speech, we do actually do parsing. So can you say something about that interrelationship, perhaps?
Sure. I totally agree that they do parsing in different modalities, but it's very different from the heuristic they needed to develop to do this. And I'm not claiming they have a full 3D representation of the objects. They might use local or intermediate parsing cues and then use them in different situations and understand how this is being done, or the vantage point, etc. So I can say, yes, definitely parsing is very important in different modalities, but I don't see how it can be directly related to the type of parsing they are doing this. It might use some audio features and some new features that are by the statistics of the stimulation they are experiencing and training on.
Scott Murray and a couple of other people at the University of Washington discovered an area in the lateral occipital complex that is selective for occluded objects, and it would be interesting to see whether it's activated by objects that are occluded but specified via your device.
Definitely. And can you think about a parallel in touch of this? Because
whether there's information for occlusion in touch, or I think so. I mean, I think that some of the same organizational principles are applied in touch. But yeah, this paper by Scott Murray is fairly recent, and there's an area in the lateral occipital complex that's specifically responsive to occluded objects. It doesn't respond when you show the occluder. It doesn't respond when you show the visible fragments of the object, but it does respond when you've got the object partially hidden behind an occluder. So
yeah, so this project
might be cool looking.
Behavioral stage, but it will be very interesting to look.
So I was interested in you doing the sort of comparison with the Parwan Sinha's work, where he's sort of moving cataracts from people and then looking at how their vision develops. And you talked about this case where you have, say, a circle and a triangle, and there's an overlap between them, and there's an initial period where his subjects say there are three objects there, one bit corresponding to the overlap and one bit corresponding to the
case of the cube. So
okay,
yeah. So the different luminances are being separated into three objects and not into a cube. And this is actually the thing that is the most difficult for them.
That's right.
Even after a year of training. And
that's right. But one thing he found, and I just wondered whether you had found similarly, was if he got one of the objects to move. So at first you show the two objects overlapping and they're stationary, and then subjects can't do the task. They can't say that appropriately that there are just two objects. But then the minute he gets one of the objects to move, instantly the people say, oh no, I see it as two objects. And I just wondered if you got a similar effect, if you had tested this.
Yeah, we didn't do it, but they use the dorsal stream in a way to train and facilitate this ventral stream function. So it's definitely something that is happening. We didn't do it. Also, motion is very problematic in a way, or more difficult using visual to auditory. It might be easier to do with tongue display or different.
And likewise with sort of long-term recognition of objects. Again, I think it was in response to your question, and when I was talking, I said that he really found that the objects that subjects could identify were really ones that they'd seen moving. And I just thought, again, sort of maybe looking at stationary images isn't so helpful. Maybe sort of you build up constancy phenomena by, as you said, sort of doing a depth, sort of, advancing towards an object and seeing that it increases in size in the visual field or in the...
Yeah, but eventually you want to try, it's like this visual illusion, but eventually you would want to try and being able to do it also when it's not moving.
Yes, exactly. I was just wondering whether...
And I think your point also, and their work and our work emphasize how much... when you don't have the training happening by the development, it's a critical part of trying to understand these other features, but it can basically go beyond what we thought is a critical period in the more pure sense. That you would say, okay, they won't be able. Actually, this is what they report is the most interesting finding of them, is that not that after 3 months they couldn't do it, but after extensive training, they would start having also not the dorsal stream, but the ventral stream ability develop. So in a way, and this is in a late age. And also our subjects are late age, even later. Of course, this is not visual experience, but they're doing the function and task and again in tens of hours. So I think it stresses the note, and it's still open whether if you have it you have the same amount of training naturally when you have vision when you're young, or what I would expect it's an interaction, and you would have a lot of more statistics, but also in a period which much more extensive, there is more flexibility.
Yes. I think it would be very interesting to try training subjects on moving stimuli, perhaps more than you do, maybe doing some sort of compare and contrast, sort of people who are trained on moving stimuli versus stationary ones, and seeing what effects happen.
Yeah.
I'm afraid we're going to have to finish there in order to scoot out in time. So can we thank the speaker and commentator again?